Yeah, you can call them identities. I call them properties off to the side. To be honest, I don't know. I use the words kind of interchangeably. I think I probably shouldn't, but in general, there are others coming that I kind of just generalize as properties. So this is the beginning. How many of these are what you would call straightforward? Like you've seen them multiple times before.
The ones that are normal.
The top ones, yeah. These ones for sure, right? The top ones. Wait a minute. I don't know about those ones. I think like the second row is more common, right? Mm-hmm. Okay, because the second row is like who is cosecant? Oh, flip sine. Who is secant? Oh, flip cosine. Who is cotangent? Oh, flip. Because remember, flip we mean reciprocal, right? Have you guys seen any of the other ones before?
Yeah.
Okay, quotient ones we've seen, right?
Yeah.
Tangent is sine over cosine. And that's actually how the cheater chart works because when you do 1, 2, 3, 3, 2, 1, all over 2 is square roots, and that's kind of awkward, but that's the way it goes. When you do that, technically, that third column, the tangent column, even though you can memorize it as square root of 3 over 3, 1 square root of 3, where does it actually come from? Well, hold on. Just let me see by raise of hands. How many of you guys think the cheater chart is the way that you best think you'll learn the unit circle, or you know it already? Okay, there's like 4 or 5 of you. How many of you guys want to know it better? 3 or 4 more? Okay, the rest of you guys, I'm worried that either you're not going to learn the unit circle, or you're going to use the circle and it's going to be hard, but that's okay. Can you guys go ahead and tell me to start when the second hand hits the 7? That'll be an easy way to go.
Go.
How long did it take me?
We were like 20.
Does that really limit you? Or your time on a quiz, on a test, on a quest, on a final exam? Okay, you get the card in the final, but still, does it really limit you, the cheater chart, as far as like slowing you down? I mean, most of you would still be like, wait, what's my name for the beginning of the paper? But pause. How long would it take you to draw the circle? Right? Now, what if you were just doing the first quadrant of the circle? Because this is technically just the first quadrant. We have our 0, we have our pi over 6, we have our pi over 4, our pi over 3, our pi over 2. Some of you might think of it in terms of 30 or 45s or 60s, right, with your zeros and your 90s. There are extra details, and you can actually do like sine of theta and cosine of theta and tangent of theta. There are extra details that might take you a little bit longer. You might write it a little bit nicer or whatever. But at the same time, to draw the first quadrant of the circle is going to take, I don't know, maybe some of you could do it really fast. You have to go ahead and draw and draw and draw and draw and draw and draw. And then you have to do like all of your different order pairs. And you have to do like each of your different angles. This is just a shortcut. Oops. This is just a shortcut with a little jingle that might be helpful to memorize or to remember. We're going to do some more unit circle practice, not right this second, but probably at the end of class today, just to see how you guys are progressing, if you're taking this seriously or not. Please take it seriously. However, we were just talking about the quotient properties, right? Quotient properties. Who is tangent? Toa! Yeah, you're right. But who else is tangent? Sine over cosine. When you do sine over cosine, SOHCAHTOA, right? When you do sine over cosine, those h's always reduce, and so we end up just with the TOA. So, where did 1 come from? Root 2 over 2 over root 2 over 2, the sine over the cosine. Maybe that's why we do sine, then cosine, then tangent, so that we can do sine over cosine to get tangent. What's root 2 over 2 over root 2 over 2? They reduce to be 1. What's root 3 over 2? Over 1/2. Well, the 2's would reduce to get root 3. Or what's 1/2 over root 3 over 2? The 2's reduce to get 1 over root 3, which would rationalize to get root 3 over So, how did I get the 0 and how did I get the undefined? I just divided. What's 0 divided by 1? What's 0 divided by anybody? 0. And what's anybody divided by 0? 1 divided by 0 is undefined. So technically, I'm always using the quotient property every time I do my cheater chart. At least when I fill in the 0 and the undefined part. I guess I kind of have memorized now. Square root of 3 over 3, 1 square root of 3. For the 30, the 45, the 60. The pi over 6, the pi over 4, the pi over 4. These ones, super important. These ones, super important. But these ones, super important as well. Now, this top row, it's great, like it's good. I wouldn't use it very often, but it's a thing. I guess you can see it. But what's at the very bottom of this table that I kind of had to lose whenever I needed to zoom in? What if I was to ask you from this table, what does sine squared of theta equal? What would you guys answer? Nice. Where'd you find it though, Spencer? Yeah, but it's not exactly how it's written. So it's not that there's an actual sine squared equals. It's sine squared plus cosine squared is 1. But with any equation, I can rearrange, right? And we did this when we were doing the practical word problems for STEM with like PERT. Because sometimes you would plug in the A and you would plug in like the P and the R and solve for the T. So you'd have to rearrange it. Start with a basic formula and then maybe rearrange it. So one rearrangement of a property up here could get us 1 minus cosine squared. Now technically, couldn't I also do 1 over cosecant squared? Is that true? Oh, no. It'd be the whole thing squared. Yeah, but the whole thing squared, 1 over cosecant, if you take sine. Wait, is that what this means? The little squared on the inside doesn't mean like double the sin. It means like the sign is multiplied by itself. But I thought that would be written as this. Well, it is. But there is this special, don't get tricked by the trig notation. There is this special notation that says a simpler way, a shorter way, a special way of writing an entire sine of a theta squared is sine squared of theta. Just a few of you are going to sometimes see a sine squared and try to go to your calculator and be like, sine squared! And it's like, and you're like, but can anybody do that? Do you have your calculator close? Hit the sine button. Can you put a squared right next to the sin? No, because sin by itself doesn't mean anything in math. But if you put a theta in there, if you put a number in there, how do I square it? If I can't put a squared right there, you gotta put big old parentheses and put a squared on the outside. If you were ever to actually want to plug in a sine squared, and guys, it's a thing, it'll show up. Hit your sine button. It doesn't let you do this special notation. You would have to use the actual drawn out notation. Now, I haven't filled this in. Maybe it's sine of pi over 2. Maybe it's sine of 5 pi over 6. Maybe it's sine of 72 degrees that's being squared. I don't know what it is. But your calculator says, you hit sine, it says, of what? Without an of, I can't do anything. So it puts a parenthesis. You say sine, it says, of what? If you need to do this squared, you're going to have to actually use the idea of what this is. So first of all, this notation means sine of theta squared. But second of all, according to the formula, I can find like a different variation if I just rearrange it a little bit. So from that, nope, I don't want to do that yet. Go back. What could I say about maybe a couple other trig functions like, I don't know, cosine squared? What would cosine squared equal from the table? Close.
1 minus sine squared.
Yeah, you gotta think about sine squared plus cosine squared is 1 and then subtract. So it'd be 1 minus sine squared. What if I was to ask for something like, what is tangent squared? You would have to go to your Pythagorean and say, how do I get him by itself? What would I get? Secant squared minus 1. Or if I was to ask for cotan squared, I could get cosecant squared. Long story short, these formulas can be used in all sorts of different ways and not just the normal ones. These formulas can get used in all sorts of ways, just not the normal ones. Or not just in one area. So that you know your okay. But here's another crazy one. Ready? What if I was to add another or? And I was to write cosine squared tan squared. How did that come out of the property table also? Where does cosine squared tan squared come out for sine squared?
The quotient property.
Yeah. The quotient property can be rearranged to be cosine times tangent equaling sine and then squaring both sides. But could some people maybe not have seen that? How could you justify, or how could you, without just like, oh, don't you see it? It's right there, duh.
Multiply cosine.
Is there any math that you could do to show why this is true? Now Nathan's saying that you can go ahead and move this to the other side, and I get that, I do. But whenever in math you start moving things to other sides, in some ways you're saying, yeah, the equals is true, when really we're supposed to be trying to prove that this is true. In geometry, I know. I'm going to start talking about proofs, and you're going to be like, I know that proofs might not have been your favorite thing, and to be honest, you probably didn't do it for as long as you should have. And those proofs are way different than like any future proofs that you'll ever hear about or see or maybe have to do in math. They're way simpler. But if you have a given and a prove verb in geometry, do you remember how you had to stay in two columns? And you had to like write down the givens and make it match the prove? Do you remember that at all? When you had to write down the givens and make it match the prove, what they were trying to teach you is that if you are building an argument for why one side is the other, the proper way of formulating that argument, unless you use this special thing called inductive proving, which is this whole other process, is to take what you've been given and work with that and make it match the other side. That's the proper system to use. So once again, if Nathan said, it's the quotient property, no big deal. He saw in his head exactly where this came from, and some people are still like, I don't know what's going on. What math could you do to the given to show someone step by step why it's sine squared without actually moving to the other side, sticking to this category, sticking with the given? What could I change? Does anybody have anything I could change or substitute or any math I could do? What could I change? What could I plug in? I can use these. I just can't rearrange them.
Tangent equals sine over cosine.
Tangent equals sine over cosine. Is that a property that you can say, hey, that's true, it's right there? Yeah? Okay. Oh, and you had to know that tangent squared of theta is who tangent is, all being squared. So you kind of had to use that notation trick of this really means that. So we pulled the squared out, changed tangent to be the quotient property. Now what? Super close. Not quite multiply. It might be so easy that you guys just don't want to say it out loud. How do you square a fraction? Square the top, square the bottom? And what's the special notation for sine of theta all being squared? And what's the notation for cosine of theta all being squared if I multiply them? And what's the math? Anybody who has like a basic understanding of math, what are they going to be able to do? Have you shown that this is that? Yeah. Without ever deviating, without ever multiplying or dividing, without taking the given and the prove and mixing them all together. So when we say an equals in math, yes, we assume it's true, unless they say something like, show that it's true, prove that it's true. Are you sure that it's true, with a question mark? Hey, what do you guys see with the directions of the next examples? Use the identities to prove the following. So, maybe I was just getting you ready for some examples that you might see. Oh, did not zoom in. There we go. So here's Adelia. going to those properties and rearranging them and saying like, I made it work. We're looking at each side of an equation as what is the given and what is the proved, and we have to work our way down step by step with substitutions or math. Substitutions means using properties or math, adding, subtracting, multiplying. We'll see a lot more in section 5.2, 5.1, chapter 5, 1 and 2. This is just an intro. But in that big old table of identities, does anyone see anything that we could either substitute with or any math that we can do to show why? That's one.
Substitute tan theta times cos. Wait, sorry. Can we substitute the tangent and the cotangent with sine over cosine and cosine over sine?
If Nathan's saying that we should substitute tangent and cotangent, tangent of theta was sine over cosine. Sine of theta over cosine theta. And cotangent with cosine theta over sine theta. What identities was he using? Uh-huh. Oh, mathematically, if that's true, oh, that's easy. Because what can I do with the sines and the cosines? I can just reduce. Because they would come together, and that's like, oh, same top bottom, it's all multiplication. No poor kittens are dying because it's all factors, and so. Dun, dun, dun. Well, that was fast. Dun, dun. But you guys, can I give you like 3 minutes to see how far you can get on the next one? Ready, set. Are you going to start with substituting? That's one way. Or are you going to start with math? Foiling, that's the other one. Can you make the left side match the right side? Can you make the left side match the right side? Pause. Powwow in your groups. Some people haven't been able to start yet. Just give them an idea. Maybe they'll like yours and maybe they won't. That's okay. It's not about whether they like it. Just give them an idea or get an idea from them. Can you start?
That can be replaced with just a 1 because SCC squared minus tangent squared is 1. And then
I just need an idea for how to start. What did you guys start by doing? Foiling or plugging in?
I know it was the
You remember? I think that was plugging in. Is that what that was? Okay.
Should we use that?
Plugging in for everybody?
Replace
No, it does.
SCC with 1 over cosine.
Okay, so everybody, yeah?
Tangent with sine over cosine.
You can start with plugging in. Just a heads up. You could have started by foiling too. Some of you don't like secants and tangents. You're like, bleh. And sometimes that'll actually help you eventually as these get fun in chapter 5. Oh, technically I'm trying to show that. I see common denominators. Do you see common denominators?
Yep.
Okay. I see 2 fractions that need to be multiplied. Do you see that? Hey, you chose this one.
Multiply across.
So on the bottom, that's just a cosine times a cosine. Are we okay with the new notation? Cosine squared looks like cosine squared of theta.
Yep.
But what's going on the top? It's an awful lot like an a plus b times an a minus b. A difference of squares. Outers and inners are going to cancel, right? First outer is a negative, inner is a positive. That cancels. A plus b times a minus b is a squared minus b squared. Stink! I need to make that 1? Now, some of you could do some illegal who knows what and be like, yeah, it's 1, wink, wink, I know what the answer is. Mm-mm. You gotta show me. Why is it 1? Have you looked at your notes yet? Have you looked at all the rearrangements of some of the properties that we were writing down just a second ago? Didn't we just talk about how sine squared is equal to 1 minus cosine squared and cosine squared is equal to you see it? 1 minus sine squared is cosine squared. It's a rearrangement of the Pythagorean property. And some of you are like, rearrangement? That's like a magical jump. Okay, fine. If you don't like that, you could have also instead gone another direction of making the sine squared 1 minus cosine squared. If you want to do it that way. Then you can distribute the negative and the 1's cancel, and that turns into a positive, and so then you can get the same thing. Anyway, whichever route you take, cosine squared over cosine squared equals? Just imagine how fun these are going to get. But it's not until chapter 5. Anyway, we're getting introduced to this idea called trigonometric proofs, aka T-proofs. You guys had seen Mrs. Regan when she visited yesterday. You could go ask her favorite topic in math. Guess what it would be? T-proofs. She tried to steal it from her daughters for homework, but one daughter liked math so much she wouldn't let her do it, and then the other daughter didn't get that much. But either way. T-proofs, they're fun little puzzles. Yeah, she came to see Mrs. Leon this week. She's down here. I think that's all the T-proofs that we better do today, because there's something else you're going to see in homework. And to be honest, we didn't even really do a T-proof. You might be like, T for trigonometry? No, it's actually T for keep the givens in their right column and keep the proofs in their right column. So we draw these little T's underneath them to say, all right, we got to show one side is equal to the other, and then we kind of have to like squish all this into one side. Yeah. Everybody has to stay in their proper place. Then we would technically get this guy down to be like, hey, guess what? He won. And oh, that needed to be 1. And then we would do a little and then we would do a Latin acronym. QE. Quod error demonstratum. Thus it has been proven. But that's way too snazzy for right now. Anyway, right triangle problems. You guys have heard of things like angle of elevation and angle of depression for a while. You should have. Maybe a little bit for 1. Tiny bit in geometry, mostly algebra 2. What if you're given a word problem or any kind of problem where you have a triangle with unknown stuff and you're supposed to solve? Could you possibly use Pythagorean theorem? Is that a right triangle sort of thing? Yeah. Okay. It's nice if you have that because a lot of you are pretty good at Pythagorean theorem. But Pythagorean theorem is only good if you're dealing only with sides. If they give you a leg and you need a hypotenuse, or they give you a leg and a hypotenuse and you need the other leg. But if they give you angles inside, some combination, you gotta go to trig. If you're looking for an angle, or if you have an angle, probably Pythagorean theorem isn't going to cut it. You're going to have to do some sort of SOHCAHTOA. You're going to probably just be picking one, sine or cosine or tangent, depending on what they've given you. Maybe CHOSHACAL, but to be honest, who would like willingly choose a cosecant if they could just do a sine flip? So I'll just leave SOHCAHTOA for now. Why? Because SOHCAHTOA says sine of angle, or cosine of angle, or tangent of angle equals. These guys have angles in their equation. This guy does not. But other problem solving clues, if they say something like angle of elevation, if you're like flying in a plane, doesn't it talk about your elevation, like how high you are? Yeah. Or if you're like mountain climbing or something, like how high you are. Change in elevation. What was I talking about? Oh, with the small group last night in Palm Springs. That's where the conference is. This older couple, really cute, loves Jesus, really sweet. They were like, you should go on the gondola. I'm like, what? go up the mountain. It's like 40 degrees cooler. I'm going to be in conferences all day. But anyway, they talk about the elevation change and how the quick elevation change, I think it takes like 2.5 minutes or something for the ride, and the temperature drops 40 degrees. 2.5 minutes, 40 degrees? Yeah, because they went up. Elevation change. Anyway, elevation, you're going up. Hey, the angle is going up, twisting, rotating up from the ground, right? Angle of depression. You're at the top of the mountain, looking down to where you started from. You're looking down, feeling down, depression. This is something that we should be used to. You depress a button, you push down a button. Depression. Angle of depression, looking down. You're in a plane, looking down at something on the ground. It's an angle of your head is rotating down, depression. Anyway. Angle of elevation or rotation up from the ground. Angle of depression and a rotation down from like a weird line of sight if you're high above something looking down. To be honest, guys, I don't think I have tons of examples of right triangle problems because you don't have like it's not as brutal as the last word problem section you guys had, which was what was that 2.7, 2.8, 2 point something? 3. Sorry, chapter 3 when you had all the weird like pert and stem stuff. Yeah, 3.5, 6. It's not that bad. It's not that bad. It sounds like it because I'm getting you ready for word problems, kind of, but it's not that bad. So, first of all, what if I just gave you a triangle and I said, hey, some stuff's missing. Can you find it, please? Is it using just sides or side and angles? Sides and angles. So, I'm not going to be able to use Pythagorean theorem because x squared plus y squared is 18. Great. Well, who's x and y? I don't know. But I can use trig. Why would I not use tangent? Tangent is TOA, and I don't know the opposite or the adjacent. That's going to be a fail as far as trying to solve. But who could I use? A sine. Let's start there. If I did sine of my angle, 60 degrees, and I probably should mark the right angle. That might help a little bit. This was a right triangle. What would my ratio be?
Sine of 60 equals y over 18.
Y over 18. AKA y is equal to 18 sine of 60. Now, if you had a calculator, no big deal. Just make sure you're in degree mode. But if you don't have a calculator, tests are going to start having calculator, non-calculator portions. Why wouldn't you be able to have a calculator? Or why would I maybe not let you have a calculator? What's 60 degrees? Pi over 3 or a unit circle 1, and sine is equal to root 3 over 2. So root 3 over 2 times 18. Isn't that going to be something you should be able to solve precisely without using a decimal approximation? Yes. But that only solves for y. Who else do I need? And how do I find it? 30, 60, 90. We could do 30, 60, 90. I guess. And then we could do like sine of 30 with x over 18. Or we could just use the other two. Or we can do Pythagorean theorem. To be honest, I think Pythagorean theorem, a lot of us would make mistakes in squaring that guy. Kind of sad but true. So then I'm just going to do cosine of 60 and say adjacent over, because it's the exact same thing, except I just need to know cosine instead of sine, which if sine is root 3 over 2, then cosine is 1 half. Love each other. Speaking of all of that, doesn't this bring us back like full circle to the unit circle? Anyway, what are you supposed to be doing with the unit circle? Finding a way that works, right? Because the point to fill in a blank anything. No, the point is to just answer random questions. So before you leave for today, if I have time, which I think I do, I'm going to give you another pop quiz to take with you. And at some point, if I were you today, tonight, I would take a picture of it and I would try to take it and see if you can do it. Take your time, that's fine. But without a calculator, maybe after studying notes, try another pop quiz tonight. Tomorrow we're going to do another one, but it's going to be timed and in class. See if you can do that. Let's go ahead and do, let's see, cosine of, how about, just do something easy like 5 pi over 6. Let's do sine pi over 3. And let's do a sample bonus of tangent of 37 pi over 4. Bye, guys. Good. You do it. Find a way. Come see me if I can help. Please let me know.